All right, well, we continue. So yeah, so this was really one of the key results from the last lecture. So in our first lecture, we were talking about G modules just as um, actions of a group G on a commutative group M by Z-linear automorphisms. But then in the second lecture, we identified the G modules with the left modules over the integral group ring ZG. So that identification in particular is a um, categorical equivalence between the category of left G modules and the category of left ZG modules. Anyway, you can totally, in every relevant respect, you can pass back and forth between those two concepts, which told us, first of all, that the category of G modules was an abelian category with enough projective objects and enough injective objects. And so therefore we could take derived functors of left and right exact functors. And then the second thing we did was we observed that so these functors, which earlier the taking invariance we observed was a left exact functor from the category of G modules to the category of Z modules, and then taking covariance we observed was a right exact functor, and then the proof is covered up here. It was really pretty easy. So it turns out that the invariance functor is Hom in over ZG of Z with trivial G action into M, and the covariance is the tensor over ZG with Z. Okay, and so what does that mean? It means as a consequence, it means that for students of homological algebra, this group cohomology and group homology is really nothing new. They are just X'd and Tors for over this where the ring is again the group ring ZG. So the nth homology group is the nth Tor from Z into M, and the nth cohomology is the nth X'd from Z into M. And so what's the point of that? The point of that is that Tor and X'd are bifunctors. They're functors of each variable separately, and that can be worked to your advantage. And so therefore, if you want to compute either a Tor or an X, then you can sort of have it either way. So for Tor, Tor is a symmetric functor. It doesn't matter what order they are. So for Tor, you can compute Tor of AB by taking a projective resolution either of A or of B. So here we can take a projective resolution of M, okay, which is what we were supposed to do in order to compute the left-derived functors of this right exact functor. But then we have to compute a different resolution for every M, or we could compute a projective resolution of Z, which, okay, that depends on G. But if you fix G, then one projective resolution of Z will give us all the homology groups for all G modules for that fixed G. And then over here, the X is not a symmetric functor. So for this, well, you could either take an injective resolution of M and apply the Hom functor to that, and then take the homology, cohomology. Or if you like it better, you could take a projective resolution of Z, take the Hom, and then take the cohomology of that. And it does sound like if you notice, I said I could do two things here, and I said I could do two things here, but one of those two things was the same thing both times. So both times if we, right, so I think this gets, so as I said, so in this case, we can use a projective resolution of Z over ZG to compute both the group homology and the group cohomology. Okay, and so the main thing that I want to do in this lecture, at least talk about, is to give you a certain standard projective resolution of Z over the group ring. Okay. Before that, there were a couple of applications. So this I went through kind of not only quickly, like really incompletely, I think. So this is just nailing down. I told you that group homology and group cohomology is actual honest topological cohomology, at least when the module is Z, of an associated topological space, an Eilenberg-MacLane space. And well, if that's true, so it's a space whose fundamental group, connected space, whose fundamental group is G, and all the higher homotopy groups are trivial. And so if that's true, then the first homology group should be the abelianization of the fundamental group. So this in particular is some confirmation of what I was saying about Eilenberg-MacLane spaces. And then intermediately, it turns out that the reason that these two things are isomorphic is because each one is isomorphic to I mod I squared, where I is the augmentation ideal in the group, right? Okay, and then the standard machinery of the long exact cohomology sequence gave us this first isomorphism that the homology is isomorphic to I mod I squared. Remember that Z as a trivial G module is isomorphic to ZG mod I. So that's one reason that comes in. And then, yeah, so I kind of sped through this last time, but it really is quite elementary to you, the way that you show that I mod I squared is isomorphic just as a commutative group to the abelianization of G is you actually write down explicit mutually inverse group homomorphisms between them. Okay. And so there it is very quickly. This is written down, for instance, I think on the Discord site, I included the link to my homological algebra lecture notes where this is. I might as well post those on ELC. Well, maybe I might as well. We'll see whether I do. Okay, so that's one application. I guess the next application that I want to do, but before I discuss the kind of standard resolution, which leads to this considerably more concrete description. I think I'm only going to have time, certainly in this lecture, I'm only going to have time to apply the standard resolution to give the description of group cohomology in terms of cochains, modular coboundaries. You can also use the standard resolution to give a down-to-earth description of group homology. I won't do that right now. But maybe if the group is nice and simple, maybe without any, maybe just by, maybe we can just directly write down a projective resolution of Z over the group ring if the group is simple enough. Okay. Okay, if the group is trivial, then Z is already projective as a ZG module. So any non-trivial group, that is not going to be the case. So yeah, so the simplest group for this purpose would be an infinite cyclic group. Okay, so I want to do infinite cyclic groups, and then I want to do finite cyclic groups. Those are the two examples that I'm going to do. Why is this helpful? Well, first of all, that's commutative, which makes the group ring into a commutative ring. Hey, I like commutative rings. I happen to know some things about commutative rings, much more, not everything, but much more than I know about a non-commutative ring, that's for sure. And so this one, it turns out, if instead of Z, we took the natural numbers, the non-negative integers in Z, the non-negative integers, then any commutative algebra class should tell you that the monoid ring Z adjoin N is just the ordinary polynomial ring in T. So these monomials are corresponding to the elements of the monoid. Well, now I'm taking the group, which is the integers of the group completion of the natural numbers, and so we get something close. Instead of getting the ordinary polynomial ring, now instead of just non-negative powers of T, we also have negative powers of T. And so I can maybe, if you like, maybe this is definitely an exercise in my commutative algebra notes, that the group ring for an infinite cyclic group is naturally canonically isomorphic to the Laurent polynomial ring, or if you like, the localization of the polynomial ring. You just invert you just invert T. Okay, so that's so this is a very, very pleasant ring in this case. It's a, in fact, it's a principal ideal domain, right? Because, wait, not a, it isn't. Wait, I'm getting confused now. Because I took, if this were a field, this would be a principal ideal domain. So what do I mean by this? It's a unique factorization domain. Let me think for a second. Okay, I didn't. All right, okay, I think I just got turned around in the moment. I did not write down that this was a principal ideal domain, so I don't think I'm using it. It's a very nice ring. It's a UFD. It's a UFD of Kroll dimension 2, so it's not a PID. Okay, so what? Also, we have this description of the augmentation ideal. The augmentation ideal is generated by differences of elements. It's generated by non-trivial element of the group -1. Okay, so although this is not a principal ideal domain, this the augmentation ideal in this case is principal. I guess maybe, you know, if I'm thinking of it as this Laurent polynomial ring, in that case, you know, under that isomorphism, the augmentation ideal is just corresponding to the ideal T-1. All right, so the augmentation ideal is principal, and the group ring is a domain. And so if any non-zero principal ideal in a domain as a module over that ring is free of rank 1, is isomorphic to the ring itself. Okay. Right. So I mean, in general, any principal ideal is isomorphic to the ring modulo its annihilator, and because we're in a domain, the annihilator is 0. Okay, so that's the helpful part. The helpful part is that in this case, almost never is it going to be this simple, but in this case it is. The augmentation ideal is itself a free rank 1 ZG module. Okay, so that's very helpful. So if you do that, then you see that just our regular old, let's see. So yeah, so we do this. So this map here is right. So this map here is the usual augmentation homomorphism, where we take every G and we send it to 1. And so the kernel of this map is the augmentation ideal, but the augmentation ideal can be identified as a module with ZG itself. And so under that identification, right, so to be exact, the image here should be the kernel here. And so the kernel here is the principal ideal generated by sigma -1. And therefore, by all the words I've just said, this is already an exact sequence in this case. Okay. So what's the point? The point is that we wrote down, you know, a priori, we're going to get like an infinite resolution of Z by projective ZG modules, but this is a finite. It's free, okay, which is even better than projective. So it's like I have a P0 and I have a P1, and that's it. So what does that mean? Well, that already means that all of the homology and cohomology groups beyond the first one are just going to be 0. Okay. All right, so it follows that if we take the, again, I'm just working from the definitions here. So how do I get the group homology here, right? So what was I doing? I was tensoring from, go back. Think about this for a second. Yeah, so the way that I compute the group homology, right? Hold on just a second. Is, so I take my projective resolution and then I apply my functor to that projective resolution, and that functor is tensoring with M. Okay, so I take this thing. Yeah, sorry. So I guess I kind of skipped a step here. So what is the homology of what in general, it's the homology of like, there we go. So it's the homology of that complex, okay? But this is really easy because I'm tensoring from ZG to things that are ZG. So of course, if I tensor M from ZG to ZG, then that doesn't change anything and I just get M again, okay? So it's just the homology of this complex. It's just 0 to M to M to 0. And this map is just sigma minus 1. Okay, well, we can compute that. So it goes from right to left in this case. And so the 0th homology is the kernel here, which is everything, which is M modulo the image. So the 0th homology is M modulo sigma minus 1 of M. This is M minus, so again, this is the augmentation ideal. So this is M minus M modulo IM. It's also manifestly the covariance. So the 0th homology is the covariance. That should always be the case. So that's good. The first homology, right, is now the homology at this guy, right? And so now it's the kernel of this map. But what's the kernel of this map? These are all the elements of M for those elements, let's say X and M, for which sigma of X is equal to X. But if sigma of X is equal to X and sigma is the generator of the group, that means that X is fixed by every element of the group. So the kernel now is the covariance inside of, sorry, the invariance inside of M, Mg, and the image here is of course 0. So that's kind of interesting. So the H1, lower H1 is equal to upper H0. These things happen, okay. And then again, for all M greater than or equal to 2, the homology is equal to 0 because the complex ends right there. And now similarly, we can do the cohomology. So this time, I guess I wrote it out a little bit better. So now instead of stripping away the M and tensoring stripping away the Z and tensoring the complex with M, now we strip away the Z and we hom the complex with M. Okay, and so we get this, and that's kind of just as easy. And yeah, I kind of want to move on, so maybe I'll go through this a little bit quickly. But again, you can check that indeed. So now it goes in the other direction, right? And so then the kernel of this map once again is going to be is going to be the invariance, and then just think for a second here. So what is hom ZG from ZG into M, by the way?
M, because you can look at like where the identity goes.
Right, because this is a free. If what's hom R from R into M, right? So this is a free module of rank 1. So this is the universal property of free modules. You send the identity element to wherever you want with no restrictions. Yeah. So this thing, each of these things turns out just to be M. Okay. All right, and so you see, it's funny. It's like basically, it's basically the same the same sequence, but now we're kind of reading it the other way. Now we're taking cohomology instead of homology. So great. So therefore, the kernel is same question as before. The kernel is the invariance. The image is 0, and then we do it the other way around, and we get that H super 1 of G of M is now going to be M modulo the image of this map. And as we've discussed, that is the, well, not as we discussed, that's basically by definition, that is the covariance. Okay, so they, it's very, very simple, and they kind of flip. Okay. Let's see. So before I leave this example, in particular, I guess we get, if I take M to be equal to Z with trivial action, in particular, we get H1 GZ is equal to Z. Can anybody tell me what the Eilenberg-MacLane space is in this case? So I don't know why I'm doing this, but I feel like it. So I'm looking for a topological space that, nice topological space, the CW complex, that's connected, whose fundamental group is the group G, which in this case is Z, and all the higher homotopy groups are 0. Equivalently, I want a connected space whose fundamental group is Z and whose universal cover is contractible. Can you think of a topological space whose fundamental group is infinite cyclic and whose universal cover is contractible? I'll give you a hint. It's not the weirdest topological space you've ever seen. I'll wait.
F1?
This, yeah, the circle. Yeah. So here the Eilenberg-MacLane space KG1 is. I'll write equal, but here I guess I mean homotopy equivalent. Homotopy equivalent. That's how well defined the Eilenberg-MacLane space is. So here, yes, why is this example working out so not completely trivial, but really nicely? Because what we're really doing is we're taking homology and cohomology of local systems, if you know what that means, on the unit circles. That's not so bad. Okay. In particular, it is true that the first homology of the unit circle is Z, of course, and that all the higher homology of the unit circle is 0, and that the 0th homology of the unit circle is Z, right? So yeah, so if I take M equals Z here, I get H0 and H1 are both isomorphic to Z, and I get that all the higher homology groups are equal to 0. Sounds good. Similar sounds good on the cohomology side. Okay. All right, so now the next one I want to do, I think I'm mostly going to leave this as an exercise. What about the case of a finite cyclic group of order n? This was really more warm up. A finite cyclic group is we can do business with that. This will come up when we do Galois cohomology and class field theory later on. So again, just to write it in a good way, so let's just say it's generated by sigma, so that sigma to the n is equal to 1. Again, the augmentation ideal is generated by sigma minus 1. Okay. I'll let that follow easily from the just basic facts about the augmentation ideal. I'll let you think about that. Right, let's see. And so my claim here, which I'll let you think about, is that the kernel, here we also have the norm element, which we only have when we have a finite group, but now we do. Okay, so just this in the group ring, it's just the sum over all the elements of the group. So my claim here is that the kernel of sigma minus 1 on the group ring is the image of the norm element, and the image of the norm element is the principal ideal generated by the norm element, which as we've discussed is the invariance of the group ring. Okay, why does that help? I guess I wrote this a little bit messily. Then you can write down a infinite but still very explicit and easy free resolution of Z over the group ring. So if you believe both of these things, then it becomes a very straightforward check. This is again the usual augmentation map whose kernel is the augmentation ideal, so it's given by sigma minus 1. Okay, so yeah, so this is also a bit of an exercise that you get a free resolution just by taking ZG in every case, and then these maps are alternately multiplication by sigma minus 1 and multiplication by the norm element. Okay, this is discussed in slightly more general terms in my homological algebra notes. In my homological algebra notes earlier, I have this ring theoretic construction that I call a Kaplansky pair. And so if you're very, very curious, you can look that up. So there's some general notion of a kind of I think it's like a pair of ideals in a ring where the annihilator of each ideal is the other ideal. And if you have such a thing, then you can do some nice thing with resolutions. Okay. So that's kind of one sort of explanation for what's happening here. Okay, and so now we come down to an exercise. And so, all right, well, all you have to do is you just have to do the same thing. I've given you a free resolution. Once again, you see that it's going to work out basically the same way, right? So to take the homology groups of M, so H lower bullet G of M. So again, I should take this free resolution and tensor it with M. And we did, I mean, much of this is the same as before. I'm just going to get a bunch of copies of M, right? And then the maps between them are either going to be sigma -1 or the norm map, okay? And so, and then similarly for, for cohomology, you're basically just going to have, you're just going to be taking the homology and cohomology of a complex. You have to pay attention to what the maps are, but each term in the complex is just going to be M itself. So that's pretty easy. Okay. And so the exercise is, okay, it's a little bit more complicated in this case. So the zeroth homology is, as it should be, the covariance, so M minus the modulo of the augmentation ideal. For all odd positive integers, it turns out that the nth homology is invariance modulo the image of the norm map. For all even positive integers, not zero, but for all even positive integers, the nth homology is the kernel of the norm map modulo the image of the augmentation ideal. You go to cohomology, and again, it flips. The zeroth cohomology is the invariance, it better be. For odd positive integers, the nth cohomology is kernel of the norm modulo the augmentation ideal applied to M, which is exactly what we were getting the even indexed homology is. And then the even indexed cohomology among positive integers is invariance modulo N of M. Okay, so you see that these things are kind of, again, the cohomology and the homology groups are sort of pairing up with each other, but with a kind of flip. Okay, so this is a good exercise. If you haven't, you really can do this exercise by Friday morning. You know, I promise. It's just straightforward. Okay, right. And so if we reflect on this a little bit, you start to see that, you know, group homology and group cohomology they're not just like analog to each other. They're not even just dual to each other in some, you know, linear algebraic sense. In some cases, they really are like kind of the same. And so this is going to be the beginning of Tate cohomology, which for a finite group, we define an infinite sequence of, a z-indexed infinite sequence of groups obtained by splicing together the cohomology groups and the homology groups. Okay, so this will, I mean, just a like level 1 foreshadowing for Tate cohomology, which will come up later. Okay. Anybody know what the Eilenberg-MacLane space is in this case? What if G was Z mod 2? So, you know, 2-element cyclic group. Can you think of a space whose fundamental group is Z mod 2 and whose universal cover is contractible? How about the first thing first? What's your favorite space whose fundamental group is Z mod 2? Well, such a space should have a 2-sheeted covering, which is simply connected. So it should be obtained from its universal covering by modding out by some involution or something.
Is RP2 an example?
Yeah, so RP2 is an example of a space whose fundamental group is Z mod 2. is the universal cover of RP2 is what now?
S2?
S2. Is S2 contractible? No, right? It's compact. No compact manifold is contractible. S2 has non-trivial second homology. Okay, so the RP2 is like halfway. We got a space whose fundamental group was the right thing, but its second homology, let's see, its universal cover had non-trivial homology. Why am I wasting? I like this, so I'm not going to apologize for it. Okay, so notice that RPN would work just as well or just as badly. The universal cover of RPN is SN, and SN is obtained as a CW complex just with a 0 cell and an N cell, right? And so in some sense, we're improving things by cranking up N because the unique non-trivial homology group is getting bigger. Anybody see what we should do? Could we push that non-trivial homology group off to infinity in some sense? Okay, well, it's fun to, I really don't, I was having trouble justifying the time. So the answer is that if a K Z mod 2 Z mod 2 Z1 space is RP infinity, infinite dimensional projective space, which is, you know, it's the direct limit of RPN when you as you vary over all n. Okay, so you build this as a CW, you know, you can build RPN as a CW complex from RPN minus 1 just by attaching one more cell in dimension n. So if you keep doing that and doing that and doing that, then eventually you'll get RP infinity, an infinite dimensional projective space. And so RP infinity is an Eilenberg-MacLane space for the group Z mod 2Z. And you notice that it's kind of infinite dimensional, right? And as is appropriate, because again, if you just put M equals Z here, you would see that you are getting, what am I trying to say? So RP infinity does have infinitely many non-zero homology and infinitely many non-zero cohomology groups. Okay, that's the answer for, that's the Eilenberg-MacLane space for a cyclic group of order 2. I'll just throw it out in the air and you can think about it. What would be the Eilenberg-MacLane space for a cyclic group of bigger order? Ask your topology friends, but there's something out there which is a generalization of projective space in the sense that projective space has the sphere as a 2-sheeted universal cover. There's something else that has the sphere as an n-sheeted universal cover. Okay. All right, any questions? Well, shoot, I don't know why I stayed up so late last night working on this, if this is all the farther that we got, but okay, now we come to the, I want to actually give you the standard resolution of Z over the group ring ZG. So I want to motivate it a bit. I have to be honest, I find almost every textbook treatment of this topic to be lacking in one way or another. Like they don't include all the details. Yeah, so they almost never include all the details, like one way or another. Or they say, you know, the proof of this is just like in algebraic topology when you show, and I'm like, okay, fine, do it. You know, so I'm not super happy with it. So anyway, so let me give you a discussion, and my discussion will explain more the parts that Harari does not explain. So he explains some of it, and what he explains well, and then he doesn't explain the other parts. Okay. So again, as we said, we really would like to have a projective resolution of Z as a ZG module. As we just saw, if we have such a thing, then we can use it to compute all our group homology and cohomology. So we have a couple preliminaries here. So the first one, which is useful aside from this, is that if I have two G modules, or again, ZG modules, if you like, then I can put Z module structures on the tensor product and the Hom, but now listen very carefully. I'm taking the tensor product over Z here. So this is the tensor product over commutative groups, and I'm taking the Hom over Z here. Okay. I do not claim that if I took I could take the tensor product if I gave myself just the right, if you think about it for a little while, you can probably convince yourself that the tensor product over ZG could be taken here, but I wouldn't get a ZG module anymore. I would only get a Z module. And similarly, here we'll see we could definitely take the Hom over ZG. That's gonna come up, but the Hom over ZG should not be a G module anymore. It should only be a Z module. Okay, so this is the subtleties that we have to start to deal with. Okay, so what is this? I mean, no problem to define. The tensor products is especially easy. I just have to tell you how G acts on a tensor, and it acts diagonally. Okay, so an element is a finite sum of something tensor something. Each of the two somethings has a G action, and you just let G act diagonally. Okay, that's all it is. So that's the diagonal action, and that's nice. I really care about the Hom. I just wanted to introduce both. And this one maybe looks kind of weird the first time you see it. And then the more you work with it, the more you're like, I love it. This is the best thing ever. Okay. So if I have a Hom between G modules, how do I let G act on this function? Well, this should be another homomorphism from A to B. So you just have to tell me where A goes. And the answer is that I have G act on the inside by the inverse, and I have it act on the outside by G. Okay, this makes sense because A is an element of A, which is a G module, so I can act on that. Then I apply F, then I get an element of B, which is a G module, then I can act by G. Okay, so this makes sense. These are just words, so I've heard this called the adjoint action, and so I call it that myself. And so yeah, this might not have been what you wanted to see, but it's the best. And so let me try to explain why. So in particular, what are the invariants here? So again, we did get a ZG module, so we can take the G invariants and then get a Z module. Well, let's just check. So in order to be invariant for all G and for all A, G dot F of A should just be equal to F of A. That's what it means to be invariant. And G dot F of A was equal to this thing. So this is the relation that we look at. And you look at this for a little while, and you're like, too many G's. As A ranges through all elements of A, so does G times A range through all elements of A. So without loss of generality, I can just substitute G of A in place of A here. Same condition. And once I do that, the thing pretties up considerably. That insertion of the G cancels out the G inverse, and so I get G F of A. And then over here, again, I replace G with GA, so I get this. And you look at this, and you're like, oh, the G invariance condition turns out to be the G equivariance condition. And so you find this lovely, lovely, lovely identity that with this G action on the Z Hom, the G invariant elements are precisely the G homomorphisms. That's just great. That's a, it's pretty, it's simple, it's used all over the damn place. Okay, so variations on this are ubiquitous. So just to drop something that some of you will have seen before, if you're trying to figure out if you have two varieties that are defined over, to fix idea, as a perfect ground field, and then you have a morphism over between those two varieties, which is a priori defined over the algebraic closure. This happens all the time. For instance, when you're studying elliptic curves, and you want to know whether your morphism is actually defined over the ground field. Anyway, you get an action of Galois on the set of morphisms between two varieties defined over a field, and it turns out that the condition for a morphism to be defined over the ground field, it should be invariant under the action of Galois. So the rationally defined morphisms are, in fact, the Galois equivariant morphisms. Okay, so again, some of you are probably nodding because you've seen that before, and some of you will see it, we'll see it later. But it's the same principle. All right, so a little exercise here. Now we move on to the second preliminary. So yeah, so let's take a left G set that is free, not free in the module theoretic sense, but really free in the sense of groups acting on sets. What does that mean? It means, for instance, that all the stabilizers are trivial. So for every G and G and every X and X, the only way that G fixes X is that G is the identity. Okay, so that's a free G set. And then the exercise is now if I take the direct sum of copies of Z indexed by my free G set, first of all, pretty easy to convince yourself that this guy has the structure of a ZG module. There's a natural G action here where G is just permuting the factors in this direct sum. And so that makes it into a ZG module. And what you, so first of all, believe that. Second of all, prove that this type of ZG module is a free ZG module. How do you show that a module is free? The best way is to find a basis. And now show that if you just choose a set of one representative for each G orbit on your free G set, okay, a free G set kind of is up to isomorphism in the category of G sets, is just going to be like a disjoint union of copies of G, one for each G orbit. So the idea of choosing a representative of the G orbits is a very reasonable thing to do for a free G set. And so if you take that set of elements, then that will give you a basis for this free ZG module. That's an exercise. Also not a hard exercise at all if you just sit down and figure it out. Okay, so now we're going to define our standard resolution, and it's a bit tricky the first time you see it. So first of all, I'm going to define E sub n to be just the direct product of n plus 1 copies of G. Note, one more copy than the index, okay? And then I notice that G to the n plus 1 is definitely naturally a G set. Again, G just acts, diagonally. So G acts on this n plus 1 tuple just by multiplying each coordinate on the left by G. It's very easy to see that this G action is is a free G action. So the only way that every non-identity element is going to move every single one of these. In particular, it's going to move each of the coordinates. So it's going to move the whole thing. So En is a free G set, and so therefore by the exercise that we just did, we just took the free Z module with basis a free G set. So we get that Pn is a free ZG module. Okay. Again, you can sort of, it's not coming in directly, like what is the rank of this free G module? Well, then you have to kind of figure out, what are the orbits? This is a free G set. How many orbits? As we'll see later, the orbits, to get one element in each orbit, there's a unique element in each orbit whose 0th coordinate is equal to 1, the identity element, right? You can act on the left by any element of G. So by that action, you can make the 0th coordinate be the identity, and then you have absolutely no control over any of the other coordinates. And so it turns out that a basis for En as a free left free left G set is going to be G to the n, one fewer copy. And so the rank of this free ZG module is going to be the cardinality of G to the n. Yeah, so now I kind of see why I didn't really need to say it, but maybe it's helpful. So the rank is cardinality of G to the n. Okay. Which is whatever, but when n equals 0, that's certainly 1. And so therefore P0 is isomorphic to the group rim itself. Okay, so now I want to define resolution between these guys. Okay, so the D0 should be a map from P0 to Z again, P0 is a free ZG module of rank 1, so it's isomorphic to ZG. This really is essentially the augmentation map. So this P0, again, just to think about it, this is a free Z module whose basis is G at basically ZG. Okay, you really can identify P0 with ZG on the nose, if you like, because it's a free Z module whose basis is G. That's what ZG is. And so this D0 really is just the augmentation map. Okay, so the elements of P0 are just Z linear combinations of elements of the group, and you just take every element of the group and you evaluate it to be equal to 1. The other maps are starting to look familiar from homology and stuff. So there's a boundary map here from Pn to Pn minus 1. This is a ZG module map. Okay, this is supposed to be a homomorphism of ZG modules. I don't know why. I think for like 1 second, I decided to put brackets in there and I realized I wasn't going to keep doing that. So, right. So let's see. So Pn minus 1 is a set of finite Z-linear combinations of these types of tuples of elements. Okay, and the same for Pn. So okay, so again, if I just tell you where it goes on a basis, then I'll be fine. Okay, and so it takes right. So it takes an n+1 tuple and it sends it where? Well, it sends it to a certain Z-linear combination with coefficients plus or minus 1 of tuples of length 1 smaller. This is an n+1 tuple. It's going to send it to a bunch of different n tuples. It's not the worst possible. And what do? You kind of omit, the hat here means we omit this element. Okay, it's kind of standard convention. And so you pull out each of the elements, and that will give you n+1 different n tuples, depending upon which one you remove, and you add them all up with alternating sign. Okay, so that's the map. And again, I'm telling you what it is on a Z basis of of Pn, and then by Z linearity, it uniquely extends. Okay, so I claim that these are ZG maps. And here's the result that I didn't even write up in my handwritten notes here, is that this works, and you do actually get a free resolution. Each one of these PNs is a free right. So PN, not oops. Each PN is a free ZG module. So and these are ZG morphisms. So the content of this lemma is that this is a long exact sequence. Okay, so the kernel of one is equal to the image of each one is equal to the kernel of the next one. Okay, so that's what we have to prove. And once you prove that, then you get an explicit free resolution, which is, in particular, a projective resolution of Z over ZG. Okay, and so I say come back to the proof later. I probably won't, but you can see. So this is proved. So the proof is in Harari. Okay, so again, some treatments otherwise, some treatments of group cohomology that I otherwise like try to not prove this lemma for whatever reason. The proof is definitely non-trivial. It's not the hardest thing in the world. It takes like maybe 2/3 of a page. Okay? But they just nothing. He doesn't prove it using anything else. He just proves it. Okay. And so maybe this is a good place to stop. So I have defined a free resolution of Z over ZG, which is what I said I wanted to do. So let me stop and ask if there are any questions here. Notice that the ranks of these free modules are increasing pretty rapidly. In fact, if G is infinite, then every one of them except for P0 is a free ZG module of infinite rank. Okay, so it's definitely not as simple as what we were doing before in the examples, where we had a free resolution of rank using rank 1 free modules. Okay, so let me go on. I'll go on. I guess I want to go on. Maybe I'll go on for 10 more minutes for today. And then if you gotta go, you gotta go. I'll post it. Right, and so let's explore the consequences here. So right, so we know that the invariants are the Hom from the group ring of Z into M, and therefore the group cohomology is the X groups from Z into M, and so therefore that's obtained by taking the cohomology of this complex. Okay. Right, and so now I just want to interpret, but what does that actually mean, right? Like I want to kind of make this as concrete as I can, right? So the first step is, well, let's look, that's supposed to be a PN, I don't know what happened there, sorry. So the first step is, well, what is Hom ZG from PN into M? Okay. Again, there's various ways of doing this. I mean, one way to think about this is that, I mean, since PN is a free Z module, this must be isomorphic to an enormous number of copies of M. Okay. Direct sum of an enormous number of copies of M, but maybe there's a better way of writing that. Okay. So now I'm going to use the thing that I said before. This ZG Hom is precisely the G invariant elements of the Z Hom. Okay, so we're going to do that. And so now let's look at the Z Hom. Okay, just using various universal properties, but Pn is a free Z module, and by the universal property of free Z modules, right? So Hom from a free Z module with a certain basis into any Z module M is just obtained as any set, map each element of your basis to any elements of M that you want. Okay, so just keeping the super G in play here, this guy, this Hom Z, is literally En, I remind you, is just notation for G to the N plus 1. Okay. So, so this is the G invariant elements of these maps. Okay, so here I'm abusing notation very, very, very slightly because this is not a, no, I'm cool. I don't think I'm abusing notation. I am taking G invariant elements here. Okay. And so let's just, what does that mean, right? So again, we have this map from a group, not necessarily from G into M. I have my G action on both sides, and so I know what the G action is here. And so yeah, so again, I'm using the fact that the G invariant elements are the equivariant functions. So again, which is, I guess, to be completely honest, I'm using that the invariants are equal to the equivariants, not in exactly the same context in which I discussed it before, because this is not necessarily a commutative group, but it's easy to see that this is still true. Okay, and so therefore, what description are we getting? We are getting a description of this Hom as the G invariant functions from G to the N plus 1 into M, G equivariant functions. And so, well, what does that mean? It means kind of the most reasonable thing that you think. So G equivariant would mean, I can act on G on the inside, in which case that's the diagonal action as we talked about before, and that's the same as acting on G on the outside. Now we apply F, we get an element of our G module. Okay, so what I've done so far is to give you a very, very explicit description of the guys in the complex that we're taking the cohomology of. Okay, so the nth term in the complex I'm calling script or mathcal kn. At the moment, the description that I'm giving you are just G homomorphisms of G sets from Gn plus 1 into M. Okay, and we add them pointwise. All right, so that's one description. And then what's the coboundary map? Again, if you just go back and track it through, the coboundary map is defined in terms of the coboundary map the D's before, and so that's no problem for whatever. Just here, I'm just notationally, I'm giving it a delta because I'm going to do something modified, and I'm going to call the modified thing a D. So, right, so what is the coboundary map? If you give me a G invariant, a G map from Gn plus 1 into M, then its coboundary should be a similar guy, but taking as arguments n plus 2 elements of G. And so the coboundary attached to the G0 up through Gn plus 1. Again, there's something here, but it's really just straightforward from what I told you, the coboundary maps between Pn, the boundary map from Pn to Pn plus 1 is. So really, I'm just think for a second. Yeah, really, I'm just taking this map. I'm just taking this map and pulling it back. Okay. All right. Right. And so that's so we get this description. So so the coboundary map comes out to be this. Okay. And so this turns out to be, so this, anyway, this is a perfectly good explicit description of what this complex is, right? I've told you what the each term in the complex is G maps from here to here, and I've told you what the coboundary map is. So you just take kernel mod image, and that gives you the cohomology groups. The thing though is that we can do better than this. Okay, and so one idea here is that the G equivariance here can be used. If you think about this, you realize that somehow I have one extra degree of freedom that I haven't taken into advantage, right? So again, a G equivariant map from Gn plus 1 to M is going to be, we can simplify that slightly. Okay, as I said, I mean, the hint there is that before I was talking about how does G act on Gn plus 1, right? The action is free, and by ranging over the G orbit precisely allows you to take the 0th coordinate equal to 1. And so therefore you can kind of use up the G equivariance by considering guys whose 0th coordinate is equal to 1. Okay, so that's I think I definitely better stop here because I have a lot more to say in terms of doing this. I mean, I'll continue, of course, in the next lecture. But the next thing that we do is we manage to simplify this slightly. So these, by the way, these are what are called homogeneous cochains. Okay, so they work, but they're not what we really want. We can define something which is just a little bit simpler and matches what you do. And so again, here's where I want to motivate a little bit more. So I'm really not doing this for real now, but there's a kind of, if you just sort of think about how you should simplify this map by taking, by using the G equivariance in order to simplify things a little bit, the first thing that you try definitely gives you something, and then you write down the types of formula that you get, and you're going to get a formula which just looks more complicated than you would like, and then you realize that if you make a kind of change of variables, then you can simplify the formula, and then that change, so that if you sort of do the wrong thing, which could naturally occur to you, the wrong thing motivates the change of variables, which gives you the right thing. And then the right thing is going to give us the inhomogeneous chain complex. So in other words, cochains and coboundaries, like you've probably seen before, to be honest. Okay, so anyway, so we have more work to do. You see that several pages are going, and then finally I'm going to define cochains and coboundaries, and the cohomology is going to come out in terms of cochains and coboundaries. But we have maybe couple pages more of work in order to get there. All right. Well, yeah. By the way, once we do this, for many purposes, you can say, okay, now I'm glad that this standard description of cochains and coboundaries, I could have just come at it the other way around. I could have just said the nth group cohomology is equal to, come at it the other way. The nth group cohomology is equal to ZNGM modulo BNGM, and I just very, very concretely define, what these guys are. And why don't we do it this way? Well, because we want to have the long exact cohomology sequence. And so, if we do it honestly, then the long exact cohomology sequence, which is being built into the delta functoriality of it all, will come for free. And then we're working a bit in order to use our explicit projective resolution in order to get explicit formulas for the cohomology groups. Okay, I think I've said plenty for today. So again, I will see you on Friday, but I remind you that Friday will be a problem session. And then we will continue with the lecture on Monday. Okay, see you soon. Bye.
See ya.